Hi everyone. Today, we, the third year mechanical engineering students of DTU from roll numbers 2K20ME211 to 2K20ME216, are going to elaborate and explain the topic of miscellaneous hydraulic machines. So, let's not waste any time and dive into the video. Happy learning!
Good evening everyone. My name is Ravi Sankar and my roll number is 2K20ME211, and in this video I will teach you hydraulic crank, its function, construction, working and its application. So you all know hydraulic crank in day-to-day life. So let's move towards the function. Hydraulic crank is a device used for raising or transferring heavy loads. So it's just transferring heavy machineries in industry. It can be used up to load 2500 kilonewton. It is widely used in loading and uploading ship, workshop and heavy industries. And next is construction and working. These are parts of hydraulic crank: tie, jib, guide pulley, jaguar, hollow vertical post. Next is construction. A hydraulic crane consists of mast, tie, jib, guide pulley, and a jaguar. The jib and tie are attached to a mast. The jib can be raised or lowered in order to decrease or increase the radii of action of the crane. The mast along with the jib can revolve about a vertical axis, and thus the load attached to the rope can be transferred to any place within the area of crane action. The jaguar, which consists of movable ram sliding in a fixed cylinder, is used to lifting or lowering the heavy loads. One end of ram is in contact with water and the other end is in connected to set of movable pulley block, and another block called a fixed pulley block is attached to fixed cylinder. So the pulley block attached to the ram move up and down, while the pulley block attached to fixed cylinder is not having any movement. A wire rope, one end of which is fixed to a movable pulley which is attached to the sliding ram, is taking round the two set of the pulley and finally passed over the guide pulley attached to the jib. The other end of rope is provided with the hook for suspending the load. For lifting the load by a crane, the water under high pressure is admitted into a cylinder of a jaguar. This water forces the sliding ram to move vertical up, and due to the movement of ram in the vertically up direction, the movable pulley block attached to ram also move upward. This increases the distance between pulley block, and hence the wire passing over guideway is pulled by the jaguar and thus rises the load attached to the hook. So this is all about the working and construction. So now its application: hydraulic crane used for lowering, workshop, foundry, loading and uploading on the ship and a railway, wagons and heavy industries. Thank you.
Good evening, I'm Ruben Matthew, roll number 212, and for the fluid systems assignment, I'll be speaking on the topic fluid coupling and torque converter, which is taken from chapter 7, miscellaneous hydraulic machinery and devices. Now, to begin with, I would like to start off with an introduction onto hydraulic coupling, which is also called fluid coupling. So hydraulic coupling is basically a means of torque transmission hydraulically. So you have two shafts, which is the output and the input shaft, which is also called as the driver or the driven shaft. Basically, you're transferring torque from the input to the output shaft without any mechanical connections, only by using a fluid such as oil. And it is used in many different applications, but in automobiles, it is used for the transfer of power from the engine to wheels. Now, coming on to the construction of a fluid coupling, it has two main elements, which is the centrifugal pump impeller, which is connected to the impeller shaft, and a turbine wheel runner, which is on the output shaft. And then there is the two split toroidal groove discs, each of which are facing each other, the small clearance in between them. And then there are radial blades to divide them into curved cells. The hollow space in between these two are filled with an oil. Now, coming on to the working, uh, the driving member rotates, and the oil is then set into motion. And due to the centrifugal action of the pump, the oil moves outwards. It is thrown outwards, and then it is redirected, and it hits the vane blades at an angle and begins to rotate the turbine, which in turn is connected to the driven shaft. And the three main parts can be seen here in this diagram. Now, coming on to the features, the inlet angles are in such a way so as to prevent shock onto the impeller, which could cause damage to the impellers. And since rate of flow and change in the velocity vector are numerically the same, the speed of the runner and the impeller are also similar, but they're not exactly the same. Now, if the speed of the runner and the impeller are same, in that condition, there will be no flow. But due to friction and turbulence effects, the angular velocity of the driven shaft, which is given by omega 2, will always be a little less than the angular velocity of the driving shaft, omega 1. Uh, Now, the slip ratio, which is given by S, is equal to omega 1 minus omega 2 by omega 1. It is 3% at peak speeds and is necessary to maintain a continuous flow, and thus there is low power loss. If the speeds of the driving and the driven shaft is the same, it is known as a stall, and the efficiency suddenly drops to zero. Now, coming on to the efficiency, the power input to the coupling is given by P1 equal to T1 omega 1. P1 is the power, T1 is the torque of the input shaft, and omega 1 is the angular velocity of the pump. And similarly, for output, is P2 is equal to T2 omega 2, and omega 2 is the angular velocity of the turbine, T2 is the torque on the output shaft. Now, the efficiency of the coupling is the ratio of the power output to the power input and is given by eta C is equal to T2 omega 2 by T1 omega 1. And the efficiency is related to slip by the equation S is equal to 1 minus eta C. Now, coming on to the graph of efficiency versus speed ratio, it is clearly seen that it is a linear graph, it is directly proportional. But after around 0.95 of speed ratio, it suddenly drops to zero because stall occurs. Now, coming on to coupling and torque factor. So these two equations right here are derived from dimensional analysis. So first equation is called the torque factor, which is given by T is equal to rho n1 square d raised to 5, which is equal to Fn. And the power factor is equal to P by rho n1 cube d raised to 5, which is equal to Fn. And it is from the first equation you can see that torque is directly proportional to the square root of n, and power is directly proportional to the cube of n, and torque is directly proportional to the square of n. Now these two equations enable us for the scaling up of homologous fluid coupling. And in fluid coupling, from these two equations, we can come to the conclusion that low viscosity fluids are generally preferred, and physical properties like density and viscosity of the oil determine the operational characteristics of the coupling. And the fluid coupling is also bidirectional because the turbine and the pump, they're very similar in structure. Now coming on to the application, it is used in diesel locomotives, automobiles, aviation, uh, marine machinery, and agricultural machineries. Now coming on to the torque converter. The torque converter is very similar to a fluid coupling, but there is slight modifications made to them. It replaces the mechanical. It replaces a mechanical clutch in automobiles. It has other uses as well. But unlike a fluid coupling, it is able to multiply the torque or divide the torque. But in the case of automobiles, it is used to multiply torque when there is a substantial difference in the speeds, and thus providing equivalent to a gear reduction. Now, coming on to the construction, it has three main parts. The first part is the pump, which is similar to the coupling, the pump impeller, which is connected to the driving shaft, and then there is a turbine runner, which is connected to the driven shaft. Then there is also the third part, which is known as the stator, which is a reaction member, and it lies in between the pump and the turbine. The stator contains guide vanes, which impinges the liquid from the driven shaft and increases the torque delivered. In fluid coupling, we know that there is a loss of energy due to high slippage, but that is not seen in the case of a torque converter due to the presence of the stator, which basically redirects the liquids and aids the pump, uh, and energy is recovered. But and unlike straight blades of a fluid coupling, torque converter uses angled and curved blades. Now coming on to the efficiency, the torque relationship can be expressed as T2 is equal to T1 plus TV, which is where T2 is the torque of the turbine, T1 is torque of the pump, and TV is the torque of the stator. And the efficiency of the torque converter is given by eta gamma is equal to T2 omega 2 by T1 omega 1, which is the same as coupling. And depending on the guide vanes, TV may be positive or negative. If it is positive, it is a torque multiplier. If it is negative, it is a torque divider. And usually in automobiles, it is used as a torque multiplier. Now coming on to the graph of efficiency versus speed ratio, you can clearly see that uh, initially for the efficiency initially is 0, and after 0.95 it also again drops to 0, and it is maximum at 0.5, and the torque ratio is maximum initially and it drops suddenly to 0 at around 0.95. And now the slip in both the coupling and in the converter represents the inefficiency of the system, and hence the energy is lost in the form of heat, and hence dissipation of heat is an important factor in these machineries, and large coolers may be required depending on the size of the torque converter. The main applications of torque converter are in automatic transmissions of automobiles, cars, buses, and even light trucks, and marine propulsion systems and industrial power transmission. That's all. Thank you.
Hello everyone, this is Rhythm Agarwal and I'm a mechanical student at Delhi Technological University and my roll number is 2K20ME213. So today we will discuss about hydraulic cranes and jigger. So let's see what is jigger and cranes. So let us first understand what is hydraulic jigger. It is a device which magnifies through a system of pulley a small movement of ram into a large movement of load. So, the jigger consists of principally of movable ram inside a fixed high-pressure cylinder and connected to a multiple pulley sheaves. So, here is an image in which we can see there are pulley, two pulleys, and this sliding ram which is fit under fixed cylinder. And there is a rope which is fixed on one end and which further moves through the various pulleys and which is free to the another end. So, a small displacement of the ram due to injection or withdrawal of the hydraulic fluid from the cylinder causes the load at the free end of the rope to experience a large movement due to magnification effect of the rope. And in daily life, we can see its various applications, and usually they are crane and lift, where control movement are needed. So now let's understand how we can use jigger in hydraulic cranes. So as we can see in this crane, there are it consists of truss that is assembly of jib, tie, and tower, and a pulley. So let's understand first this image. Here we can see that there is a horizontal jigger present at the bottom, and there is a rotating platform above this above this jigger. Then there's a crane tower which is attached to the rotating platform, and which is further attached to the pulleys, various pulleys, and on these pulleys we can see a rope which is connected with the help of tie. To support this whole system, there is a jib, and on the on the wire we can see there is a hook is there. So the displacement of the ram in the jigger is magnified by the pulley system of the jigger. The result is a magnified movement of the hook on the crane. So now so in this, jigger is operated by a water hydraulic system. This displacement of the ram, as I said, is in the jigger is magnified by the pulley system. Now let's see what are the further things in this with the help of jigger we can operate. That is lift. So in hydraulic lift, we can use the jigger in the same way as a crane to lift the carriage vertically. The jigger is fixed with the ram working downwards so that will be supported by the cable suspension system. So as we first, let's see what is this image telling to us. There is a horizontally jigger system at the bottom, and similarly as we discussed in crane, it also works same. And there's a wire attached to the pulleys. Just a second. Yes, there's a wire attached to the pulleys, and it is further connected to other pulleys, and at last it is connected to cage or cabin, which we can move in a vertical direction. So a small movement in this jigger may lead to the large movement in this cage. So the jigger is fixed in the ram working downwards so that its weight will be supported by the cable suspension. The carriage moves in the guides and is suspended from the top, and sliding balance weight are used to balance weight of the lift and its loads. Now let's see how we can use these cranes and lift in present era. In modern hydraulic cranes and lift, we can see this truck which contains a telescopic hydraulic boom which is connected to hydraulic cylinder, then operator's cabin which can move this wire in various directions and dimensions, and it can also rotate 360-degree. Then on the other side we can see the lift which also works on a hydraulic system, not not with the help of jigger, but with the help of electronic devices. Now let's see how this works. So in hydraulic cranes, modern hydraulic cranes use the oil hydraulic system. In this, hydraulic devices such as wings and rams perform the work, and modern electronic devices are adopted for the control of the devices. There are various parts are present like main boom, in which large arm, sometimes of telescopic nature, mainly responsible for lifting. Then there is a pumps, where very heavy weight placed at the back of the in pumps, hydraulic pump system usually double gear or variable displacement pumps. In counterweight, there is very heavy weight placed at the back of the cab to prevent the crane from tilting during lifting operation. Rotax gear. In this, a gear system is placed below the cab that allows the boom to move sideways. As I mentioned in previous slide, in this, uh, with the help of electronics devices, operator can operate this system in various directions: vertically, horizontally, and or 360-degree, and other directions also. And there is outer rigger supports which suppose device is provided to the wheelbase to keep the crane balanced. And at last there is wing, hydraulically operated device to pull in or let out the wire rope attached to the hook. Now let's see how hydraulic lift works without the jigger. In a hydraulic lift, the car is moved by the hydraulic hoist or piston attached to the car floor structure. The lift is activated through an pumping system. As we can see, there is a fuel tank or a reservoir which which provides oil to the pumping system, which we can start with the help of motor. So how it is, as it is mentioned, oil is pumped from the reservoir into the base of the piston in the cylinder. An electric motor pumps oil into the cylinder through a gear pump to move the piston, which in turn smoothly lift the elevator car. So from this we can understand how the hydraulic system can help us in our daily life, like cranes and lift, and how jigger can help to make huge distance with the help of small distance in a hydraulic cylinders. Thank you.
Hello everyone, this is Rishabh Modi, 2K20ME214. My topic is regenerative flow pump. So, first of all, what are regenerative flow pumps? Regenerative flow pumps are rotodynamic pumps that are capable of high heads, giving high heads at low flow rates. This pump is unique in design and operation as it combines the main characteristics of centrifugal pumps and also some features of rotary displacement pump, peripheral pump, friction pump, side channel pump, traction pump, and vortex pump. A similar turbo machine used for compressing air is called regenerative flow compressor. An RFP consists of essentially a disc-shaped impeller, as you can see in this image, with a large number of small blades cut in a small band in uh, in the rim. The number of vanes are usually around 120. Uh, the In the standard design, the vanes occupy less than about 20% of the radial space of the impeller. The vanes are cut on both sides of the impeller disc through machining. The vanes come in many arrangement patterns, and the nature of the vane spacing and arrangement on either side of the impeller may be same or different. Web pieces of the curve profile span the vanes. Uh, you can see the impeller assembly and some details of the vanes and the surrounding channel from this image. Now, coming to the flow in the channel. When the impeller is rotating, the vanes push the flow between the two adjacent in the direction of rotation. Due to the shear of the web portion of this cavity, a lateral flow is also formed on the side channel. The unique shape of the flow channel with its two interconnected side channels uh, generates a vortex flow in the two cells, as you can see in the diagram. On each side of the web, the interaction of the tangential and flow due to the vanes and the vortex due to shear action causes a helical flow in the channel. See, this is helical pattern. Due to this flow pattern, a liquid element gets into the space between their vanes many times in its passage from inlet to the outlet. In each interaction with the impeller, some energy is transferred to the fluid element through the vane. Each passage through the vane can be considered as an equivalent to a stage in the conventional centrifugal pump. Thus, the fluid element in an RFP is multi-staged in its helicoidal path, and this enables the pump to generate high heads at low discharge, and moderate speeds of RFP leads to a low specific speed of these machines. From these, you can analyze that how a rotary pump is capable of giving high heads at uh, you know Now, the regenerative turbine impeller can pump fluid with up to 40% in trained gases without damage from cavitation or performance loss. Uh, so, as you can see, if a regenerative impeller have 40% gas or a 60% liquid, it will still not cause any cavitation. And if you take the case of a centrifugal pump, it will definitely be aroused with problems and with cavitation, since it cannot allow gas in liquid. So you can see that this makes regenerative flow pump a great solution where cavitation is a concern.
Hi guys, this is Rishi Maheshwari, roll number 2K20 ME215, and today I'll be talking about hydraulic accumulators and hydraulic intensifiers, wherein I would be explaining about with the diagrams and then telling you about the formula. So now there are different types of hydraulic accumulators, namely simple hydraulic accumulator and differential hydraulic accumulator. Now, what a simple hydraulic accumulator actually means, that is, it consists principally of a high pressure cylinder in which the ram can move. So, as you can see on the left, that there is a high pressure cylinder, and then there is a ram, and it can move up vertically, up and down. Then you can see that on the left hand side there is an inlet, and on the right hand side there is an outlet for the liquid under pressure to move around. When now how the process actually goes, when the load on the pump in a hydraulic system is reduced or rejected, the high pressure liquid flows into the accumulator and causes the ram to move. So that is the initial part of the simple hydraulic accumulator. After that, a resistance load on the movement of the ram is provided either through a dead weight or in the form of a compression string. This arrangement keeps the liquid in the accumulator under the desired high pressure. When needed, this pressure liquid from the accumulator can either be released through the outlet to the chosen hydraulic machine or device. Then we have the commonly used types of accumulators, and these can be classified as raised weight type, spring type, metal bellows type, and compressed gas type. Right. So moving on to the differential hydraulic accumulator. As you can see in the diagram, that it is a bit complex as compared to the simple hydraulic accumulator, and but the basic structure of both of them is the same. So it is actually a variant of the common type of accumulator described as before, and has the specific advantage that a relatively high pressure can be obtained by a comparatively small load on the ram. So earlier, if we were getting a certain amount of pressure from a certain amount of weight, here we are getting more pressure with lesser weight, which makes it more efficient. So now this device also consists of a fixed ram in which the introduction of a brass bush is makes the lower portion larger than the upper portion. So here a loaded cylinder slides on the fixed ram. As you can see that in the middle we have the ram, and on the right hand side we have the two loads which are fixed. Here the liquid under pressure is admitted through the fixed ram and fills the annular space between the fixed ram and the cylinder available above the top of the bush. The liquid here can enter and leave through the valve controlled openings at the bottom of the fixed ram. Right. So moving on to our next part, which is the hydraulic intensifiers. Now, what are hydraulic intensifiers? A hydraulic intensifier is a component that converts the low pressure from a cylinder into the high pressure in a smaller cylinder. Sorry. Intensifiers consist essentially of two different size cylinders. As we can see in both of them, that there are two cylinders, one inside the other. So here there are also two different types, namely the simple hydraulic intensifier and the coaxial hydraulic intensifier. So talking about the simple hydraulic intensifier, it consists of a common piston rod which connects the pistons of both the cylinders of a different bore. Here the lower pressure fluid acting on the larger piston exerts a force that is transferred mechanically by the rod to the smaller piston. So as you can see here that there is a smaller piston and there is a larger piston. So in the diagram, you can see that the higher pressure discharge is nearer to the smaller cylinder and the lower pressure hydraulic liquid is in the larger cylinder. Right. So in hydraulic, right. One thing in hydraulic circuits, intensifiers are also known as boosters. Right. Going on to the coaxial type of intensifier. Another form of intensifier which we are talking about here is the coaxial hydraulic intensifier. This arrangement consists of a fixed cylinder, a movable hollow cylinder, ram, and a fixed ram, which are all listed down in the diagram. Initially, the low pressure liquid enters through the fixed ram and enters into the hollow of the movable ram. So one of them is a movable ram and one of them is a fixed ram. Now, the low pressure inlet valve is closed and the low pressure liquid supply is let into the fixed cylinder that pushes the sliding ram. So here the liquid is doing the work, which means that the liquid is moving the piston up and down by causing pressure. Now, this action, as you can see, is similar to a syringe, a medical syringe which is used to inject something. Uh, Here, the ratio of the area of the outer fixed cylinder to the area of the fixed ram is the intensification ratio of this device, which is a very important parameter. Right. So now moving on to the formulae. Now there are four different formulae for each of the accumulator and intensifier. So one for each. In the first one, we have W equals pi d square by 4 times P, where we have W as the weight and diameter, D as the diameter, right? Next, we have the differential hydraulic accumulator. This would be a bit more complex, as we saw in the diagram itself, that it's a bit more complex than the simple hydraulic accumulator. Here, if we have the area as pi by 4 capital D square minus small d square, capital D being the diameter of the larger cylinder, small d being the diameter of the smaller cylinder, then the pressure can be calculated as weight upon area, which means weight upon pi by 4 d square minus capital D square minus small d square. Next, we have the simple hydraulic intensifier. Right. So in this, we first create an equation which is P1 pi by 4 d1 square equals P1 pi by 4 P2 pi by 4 d2 square. Here we let the suffixes 1 and 2 denote the larger and the smaller cylinders respectively. So for the small cylinder velocities, that is when there is no acceleration head. So here we take into account that there is no acceleration head. From this we get P2 equals P1 d1 by d2 whole square. Then we have the last, which is the coaxial hydraulic intensifier. Here we go for P1, which is the pressure of the lower volume and the lower pressure supply, and P2 being the higher pressure supply pressure. A1 is the area of the larger cylinder or the fixed cylinder, and A2 is the inside cross-sectional area of the fixed ram, which is inside the cylinder D2. So from here, we can get that the delivery pressure at the outlet becomes P2 equals P1 A1 by A2, 1 minus epsilon by 100 whole square. Now, what is epsilon? Epsilon, we are taking into account here that if, however, there is frictional effect amounting to epsilon percent at each of the packing of the ram from equilibrium considerations of the moving ram to at any position, thus we take into account the losses, which means we have to take into account this particular meter, which is the 1 minus epsilon by 100 whole square. Right, so that was it for hydraulic accumulators and hydraulic intensifiers. Thank you very much.
Hi, I am Rishiraj Tagore, roll number 2K20ME 216. Today, we'll be talking about two topics, torque converter and hydraulic press. So, torque converter. It is a modified form of fluid coupling. Like fluid coupling, the torque converter normally takes place of mechanical clutch, allowing the load to be separated from a power source. Unlike a fluid coupling, however, the torque converter is able to multiply torque where there is substantial difference between converter or the input and output rotational speed, thus providing the equivalent to the reduced gear. A torque consists of three main components: a pump impeller, connected mechanically to the driving shaft, a stator, usually known as a reaction member, and a turbine runner connected to the driven shaft. These are positioned in the middle of the flow from the impeller and the runner. The stator has guide vanes that change the direction of the liquid impinging on the runner and thus causes the torque delivered to the driven shaft to be higher than the driving shaft. In a fluid coupling, under conditions of high slippage, the fluid flow returning from the turbine to the pump opposite the direction of pump rotation. This leads to a significant loss of energy. Under the same condition in torque converter, the returning fluid will be redirected by the stator so that it aids the rotation of the pump instead of impeding it. This leads to recovery of much of the energy in the returning fluid and addition to the energy being supplied to the pump itself. This action causes a substantial increase in the mass of fluid being directed to the turbine, producing an increase in the output torque. Unlike the radially steered blades used in fluid coupling, the turbine and stator of the torque converter use angled and curved blades. The shaper of the blades is important as even minor variation can result in significant changes on the performance of the device. Now we'll be talking about hydraulic press. It is a device where smaller force is used to provide a much higher force or purpose for the purposes of providing compressive or lifting force. This represents the relationship between applied force and output force based on the principle of hydrostatic systems. Working devices have been developed and the hydraulic presses have been used in a stationary industry device as a stationary industry device for providing large compressive forces. Joseph Bramah is credited as the inventor of hydraulic press. A schematic hydraulic press diagram is shown here. The ram is activated by a pump, providing the hydraulic pressure that causes a displacement of a movable platform. The materials placed between stationary platform and movable platform undergo high compressive forces or pressures that causes a displacement of the movable platform. The materials placed between stationary platform and movable platform undergo high compressive forces. Common industrial use of hydraulic presses include compression forming, blanking, forging, and punching. In a hydraulic press shown here, the movable platform acts directly against the object to be passed, and the stationary platform takes the reaction load and transfers it to the foundation. This type of press is known as direct type hydraulic press. Similar to the principle of hydraulic press, the arrangement of ram working in a cylinder under hydraulic pressure creates pump, which finds use in many industrial applications. This includes hydraulic jack and simple hydraulic lift. If the stationary platform in the press is omitted, the device acts like a simple hydraulic jack or simple hydraulic lift. The other diagram shown here is of inverted type hydraulic press. In this, the plunger, under hydraulic pressure created by a pump, acts vertically downwards in the pressing action, and the reaction force is directly transmitted to the foundation. After the pressing job is over, the return weights assist in quick return of movable plate to the initial position.